Hi everyone, I'm Kai, and today I want to talk about a very common problem in machine learning: catastrophic forgetting. Think of it as the model is very forgetful. And I will show you a simple experiment where this happens and how adding one extra brain inspired term to the loss function can make the model forget less. Let me start with something simple. Imagine you are learning badminton. When you first learn, your coach might teach you forehand and then backhand as two separate skills. You practice each stroke again and again in isolation. But in a real match, the shuttle doesn't politely tell you, "Hi, I'm a forehand now." You have to react to whatever comes and switch smoothly between skills. Humans by nature can learn new skills without overwriting the old ones, and we can call on the right skill at the right time easily. Now, what happens when we do something similar with a neural network? Here, let me show you an experiment where we split the MNIST digits into five mini tasks: 0 and 1, 2 and 3, 4 and 5, 6 and 7, and 8 and 9. We then train a network to classify these digits task by task instead of training all of the digits at once. The procedure is straightforward. We train the model only on the first task, distinguishing 0 versus 1, until it does well. Then we move on to the second task, 2 versus 3, using the same model. After every new task, we test how well it still remembers the earlier and the current ones. We repeat this through all five-digit pairs. This way of training the model, where it keeps getting updated with a new task over time, it's called continuous or online learning. It's closer to how the real world works, where we constantly have new information, new rules, new uses, and new distributions. This is very different from static or offline learning, which is a more common practice where you train once on the full data set and then stop and deploy. Let's see the results. If we train the same model statically on all digits at once, it reaches around 85 accuracy on average. But if we train it sequentially, task by task, by the second steps of the sequential training process, when learning the label 2 and 3, it has already completely forgotten what it learned in the first step on digits 0 and 1. This is known as catastrophic forgetting. Formally, catastrophic forgetting is the phenomenon that artificial neural networks tend to rapidly and drastically forget previously learned information when learning new information. So, why this is a big deal? First, deployed systems must update as the world changes. Again, we have new information, new laws, new user behaviors, and new safety constraints. Second, we can't afford to retrain huge models from scratch every single time. It's too expensive. Third, and most importantly, we don't want the models to forget safely critical behaviors that we previously trained on. To get inspiration on how to solve this, I turn to neuroscience and specifically the free energy principle by Carl Friston. Before I explain the principle, let me start with a weird visual illusion. Imagine a white plastic face mask. From the far, it obviously looks like a normal convex face sticking outwards. Now, we slowly rotate the mask, and at some point, you know you are looking at the hollow back of the mask. It should be concave, but your brain stubbornly keeps seeing a normal face bulging outwards. Part of you know it's hollow, but you see it as a convex anyway. Why? According to the free energy framework, your brain isn't passively receiving information about the world. It is actively generating predictions about what should be out there and then uses the sensory input to merely check if those predictions are right. In other words, the brain tries to minimize something called the free energy, which you can think of as a measure of surprise or mismatch between what it expects and what it senses. Lower free energy means the brain's internal model fits the world better. Mathematically, free energy equals to complexity minus accuracy. Complexity means how much does the explanation distort or violate my prior beliefs about the world. Accuracies, on the other hand, means how well does my explanation fit the sensory data. If I push too hard on accuracy, perfectly fitting every noisy detail, I end up with a very complex, overfitted model that contradicts my priors. If I cling too tightly to my priors, I ignore real evidence and my accuracy drops. The brain tries hard to seek a sweet spot, minimizing free energy by balancing prior beliefs and new observations. Think of the brain as having a theory maker and a movie renderer. The recognition model proposes a theory about what's out there. The generative model tries to render what that theory would look like on our senses. They've learned over time to use the same vocabulary of causes. When something new happens, they bounce back and forth, propose, render, compare, and tweak until the rendered scenes and the actual scene line up as well as possible without breaking the prior expectations. That quick back and forth is perception. Slowly updating how they propose and render, on the other hand, it's called learning. They both share the same goal, which is to reduce uncertainty by building a better internal model of the world. Now, back to the illusion. The truth is the light and shadows on your retina suggest a hollow concave face, but that clashes with one of your brain's strongest priors. Faces usually stick out. From a free energy perspective, the brain compares two explanations: a concave face with normal lighting, or that there is indeed a non-convex face with somewhat unusual lighting. And the brain chooses the explanation which minimizes the total free energy. Because the faces are convex prior, it's so strong, built from a lifetime of experience, the brain would rather assume something unusual about the lighting than to accept an inward face. That's why the mask still looks convex even when you know it's concave. So, how can we bring this idea into a neural network? I asked two questions. First, when the LoRA adapted model learns a new task and starts forgetting the original one, how does that show up in free energy? Basically, how surprised the model is by the original labels. Second, can we use a free energy based regularizer to constrain the LoRA updates and reduce forgetting? Instead of using images, I use a simple synthetic data set where inputs X are real value vectors of length 20. Task A depends on only features 0 to 4 with labels given by a noisy linear threshold. Task B depends on a different subset, features 5 to 9, with its own weight vector. The remaining features are random noise just to make the problem a little bit more realistic. Step 1. I start with a small 3-layer feed-forward network as my base classifier, and I train it only on task A. Concretely, it is a MLP with a first fully connected layer from 20 input features to 64 units with a value, a second layer from 64 units to 32 units with a value, and a final layer from 32 units to 2 output for binary classification. This base model is the original objective the system should remember, and I train it until it reaches high accuracy on task A. Step 2. I freeze the base model and attach a LoRa adapter to the final layer. Now, I train only the LoRa parameters on task B. This is like learning a new task by only adding a small extra circuit on top, without rewiring the whole brain. LoRa has a strength parameter equal to 0, means we are using only the original task A model. 1 means we are fully using the task B adapter. By sweeping this strength from 0 to 1, we smoothly move from relying only on the original task A model to relying fully on the new LoRa adapter trained on task B. So why did I use LoRa in the first place? Full fine-tuning changes all the parameters, which is expensive, and in this setting, I don't have the infrastructure to fully retrain the base model. LoRa instead freezes the base model and only trains a small adapter. That's cheaper, and it works even when the base model itself can't be retrained, and gives us a clean handle on how much we are changing the original behavior. Here is a first look at what happens. At strength 0, when we use only the original base model, Class A accuracy is about 95%. But as soon as we start missing in the LoRa adapter at strength 0.5, Class A accuracy collapses to around 5% and it stays there even at strength 1.0. So even though we are only training a small adapter, once we commit to new task B adapter, the model has essentially forgotten task A clear case of catastrophic forgetting. On task B, even with the LoRa adapter fully trained at strength 1.0, accuracy is only about 51%, which is barely better than chance. So the model isn't doing task B very well. To connect this to free energy, I define a simple quantity. Given logit C and labels Y, I use the negative log likelihood, where P comes from the softmax of Z. So F is high when the model is surprised by the label and low when it's confident and correct. With this formula, I measure F on task A labels and on task B labels and its divergence as I increase LoRa strength. Take note that Fe divergence equal to free energy of B minus free energy of A. So if the free energy divergence is greater than 0, it means that model is A bias. If it's less than 0, it means that the model is B bias. Let's look at what free energy is telling us. Top left, this is the free energy difference between task B and task A. At low LoRa strength, it's strongly positive, so the model finds task B labels much more surprising than task A. As we increase strength, it crosses 0 around 0.4, that's roughly neutral, and then becomes negative, meaning meaning the model is now more comfortable with task B than task A. On the top right, this alignment score is 1.0 at low strengths. It means almost all samples still look like good task A explanations. Once we go past about zero point 0.6, it drops to 0, meaning the adapter has fully shifted the model to the new task B. On the bottom left, here we compare the free energy distribution on task A labels at two extremes. With LoRa strength equal to 0, everything is tightly clustered near 0. Those labels are very unsurprising. With strength equal to 1, the same labels spread out to much higher free energy values. The model now finds them highly surprising. Lastly, at the bottom right, this line graph shows the accuracy directly. Task A stays highs up to around zero point 0.4, then collapses to almost 0. Again, this is catastrophic for guessing. Task B accuracy, it's only moderate across all strengths. It improves slightly as we turn the adapter up, but it never becomes very high. So overall, as we increase LoRa strength, Free energy and accuracy both tell the same story. The model gradually stops explaining task A well, even though its performance on task B is only modest. Let's move to part 2. Can we control this forgetting by regularizing the LoRa adapter? In practice, a common way to fight catastrophic forgetting is to add a regularizer. The idea here is to add different penalties on the weights so that the adapter can still learn task B but doesn't drift too far and destroy the original task A behavior. Before we draw deeper, let's understand what a regularizer is. In machine learning, regularization means adding an extra term or penalty to the loss function to shape how the model learns. In my setting, this penalty is meant to stop the model from totally forgetting task A while still learning task B. There are two classic and common regularizers. First, L2. We penalize the square of the weights. This tends to keep changes smooth and moderate. Second, L1. We penalize the absolute value. This encourages sparsity. Many weights become exactly zero, so only a few dimensions change strongly. In this experiment, I introduced the regularizer, which is the free energy based regularizer. The idea is instead of penalizing the weight size, we penalize high surprise on task A labels. So the loss will be equal to the task B loss plus lambda of the free energy of task A. Here is the results of my experiment. On the left is task A accuracy across LoRa strengths. At strength 0 to zero point 0.8, all methods are almost perfect around 0.99. When we push LoRa to strength 1.0, they start to separate. For no regularizer, it crashes to about 0.45. Again, it shows forgetting. For L2, which is the green line, it drops, but only to about 0.71. For the free energy based regularizer, it does even better, keeping task A around 0.82. For the L1, which is the orange line, it stays nearly 0.99, basically signaling no change. So, free energy preserves task A much better than no regularizer or L2, while L1 avoids forgetting mostly by not really letting the adapter change at all, which we will see more clearly later. On the right, it's task B accuracy. At low strengths, all methods hover around 0.51, basically just above chance. At strength 1.0, no regularizer, Fe, and L2 all gives a modest bump to about 0.57 to 0.59, so they do learn task speed a little bit. With Fe very slightly ahead if you zoom in. L1, however, stays flat at around 0.51, showing almost no learning on the new task. So FE achieves the same or slightly better task speed improvement as the other active methods while still retaining task A much better. This plot shows the FE divergence, how much more surprising task B labels are compared to the task A. For no regularizer, L2 and Fe, as we increase LoRa strength from 0 to 1, Fe divergence steadily drops from about 7.2 down to almost 0. That means that the model gradually goes from being very strongly A biased to treating A and B as similarly unsurprising. In contrast with L1, which is the orange line, the curve is almost flat at 7.2 the whole time, so the adapter barely changes the model, consistent with the lack of learning we saw earlier. To check this isn't one lucky run, I repeated everything across multiple random seeds and ran significant tests. The bar shows the mean, and at the bottom, you see the 95 confidence intervals and the circuit p values are all extremely small, which means these results are statistically significant. The pattern is the same as before. None forgets task A the most. L1 basically freezes the model. L2 sits in the middle, and the FE regularizer consistently gives the best trade off between keeping task A and learning task B. So, what did we learn? First, catastrophic forgetting is a core challenge for continual learning. Even with LoRA, if we fully adapt to a new task, we can destroy performance on the old one. Second, adding regularization to the LoRA adapter is a practical way to control this, but we can still do better. Third, a free energy based regularizer seems to let the model learn the new task while keeping surprise on the old task low. For future work, I would like to scale this to larger models and more realistic data sets, explore alternative ways to measure free energy, and compare this approach with other methods such as interleave training. To wrap up, why do all this matter? First, real world models don't live in a lab. Once they're deployed, they keep seeing new data, new users, new rules, new behaviors. They have to learn continuously without forgetting the behaviors we care about. What I've shown you is that a free energy based regularizer can help with that stability and plasticity trade off. And finally, I like that this isn't just a random trait. It's a small step towards bringing the ideas from neuroscience into AI. We are using a principle inspired by how the brain manages surprise to shape how a neural network learns. If we can keep pushing in this direction, we may get models that are both more robust in deployment and more brain like in how they adapt over time. I hope you learned something today. Thank you.